Welcome to this week's lecture. This week we're going to finish talking about the Laplace transform. The first thing you may notice is this week we only have 26 slides. That's because some of the material this week is quite difficult, so I'm going to try not to give you too much to think about this week. This week we're going to be talking about using the Laplace transform to solve differential equations which have discontinuous forcing functions, and we're going to look at the convolution integral. So far in this course we've looked at differential equations where all of the functions are nice continuous functions, but that's not a typical situation in engineering. In engineering, for example, let's suppose we have some machine, the machine is switched off, then we might switch the machine on, and then we might switch the machine off again. The input function we can imagine is 0, between 0 and let's say sometime 10. And then when we switch the machine on, our function might be equal to 1, and then we might switch the machine off again. How would we solve a differential equation where we're switching the machine on and then off again? In other words, one of the functions in the differential equation is a discontinuous function. For example, solve y double prime plus 4y is equal to this function f, which is equal to 0, 1 over 5 t minus 5, and then 1. This function is not discontinuous, but it is piecewise defined. It's 0, and then it slopes up, and then it's equal to 1. And just to make our calculation easier, we're going to assume that both initial conditions are 0. The first thing to do is to write our function f in terms of the unit step function, which we talked about last week. The function starts at 0, so we start with 0. Then we have a change happening at 5, so it's going to be something multiplied by u5, and the something is function on the right minus function on the left, or 1 over 5 t minus 5 on the right minus the function on the left, which is 0. And then we have another change happening at 10. So we're going to have something u10, and the something is function on the right, which is 1, minus function on the left, over 5 t minus 5. And we can simplify this like this. Let me remind you of two formulae from previous lessons. First of all, the shifting formula. The Laplace transform of the unit step function uc multiplied by f at t minus c, and it's important to note that we have the same c here and here, is e to the power minus cs multiplied by the Laplace transform of f. And that's what we have here. We have a unit step function, u5 multiplied by some function with t minus 5, 5 and 5. And then in the second term, we have 10 and 10. So we can use the first function. And I'll also remind you that the Laplace transform of t is 1 over s. So take the Laplace transforms of this differential equation using the formula at the top. You can check that this is s squared plus 4 capital Y is equal to 1 over 5 e to the power minus 5s minus e to the power minus 10s divided by s squared. Or divided by s squared plus 4, we get a function, we get a formula for capital Y. If we can find the inverse Laplace transform of capital Y, then we've solved our initial value problem. So this section is about how can we find inverse Laplace transforms of complicated things like this. What we do is we look at the function and we pretend that all of the exponential functions are not there. Let's pretend e to the power minus 5s is not there. Let's pretend e to the minus 10s is not there. Let's suppose we just have a 1 at the top. And let's suppose that the 1 over 5 we don't need, we'll do this later. Let's suppose instead of the function capital Y, we're looking at the easier function capital H, 1 divided by s squared over s squared plus 4. Then you will note that capital Y is 1 over 5, e to the power minus 5s capital H, minus 1 over 5, e to the power minus 10s capital H. And using this formula again, remember the Laplace transform of the unit step function multiplied by, in this case, small h at t minus c is e to the power minus cs capital H, this shifting formula. But that's exactly what we have for y. Forget about the 1 over 5. We have an exponential function multiplied by capital H. Again, forget about the 1 over 5. We have an exponential function multiplied by capital H. If we can find the inverse Laplace transform of capital H, then we can use this formula to find the inverse Laplace transform of capital Y. If we can find small h, then we can find small y. We know how to find the inverse Laplace transform of a function like capital H. We can use partial fractions. I'm going to leave it for you to check that capital H is 1 over 4 over s squared minus 1 over 4 over s squared plus 4. We can find the inverse Laplace transform of this function. The inverse Laplace transform of 1 of s squared, we know this, we can find this on our table of Laplace transforms. 1 over s squared plus 4 is not on the table, but 2 over s squared plus 4 is on the table. So I'm taking 1 over 8 outside, and I'm leaving 2 over s squared plus 4 inside the inverse Laplace transform. This is just t over 4 minus 1 over 8 sine 2t. Now that we know small h, we can use our shifting formula to find small y. Here's the formula at the top. Now we know small h, we can use this formula to calculate small y. Small y will be 1 over 5, u5, multiplied by h at t minus 5, minus 1 over 5, then u10, h at t minus 10. And because we already know small h, we can write down small y. This is the main idea in this section. Let's do another one. Solve y double prime plus 3y prime plus 2y is equal to this function, which is equal to 1 between 0 and 10, and then equal to 0 after 10. We can imagine we have our machine which is switched on for the first 10 seconds, and then we switch the machine off. We're going to assume that y of 0 is 1 and y prime of 0 is 0. Because our function is 1 minus u10, we can use the Laplace transform to find that s squared plus 3s plus 2 capital Y minus s plus 3 is equal to 1 minus e to the power minus 10s divided by s, which I will leave for you to check. We can rearrange this to find a formula for capital Y. And then we want to find the inverse Laplace transform of this function. What we're going to do is we're going to split this up into some easier functions. First of all, let's suppose the minus e to the power minus 10s is not there. We have an easier function, s squared plus 3s plus 1 divided by s squared plus 3s plus 2. And then we're going to look at the second part, forget the first part, and then instead of minus e to the power minus 10s, let's suppose this is just minus 1. And we can have minus 1 over s squared plus 3s plus 2. Precisely, if we define capital G and capital H like this, then capital Y is capital G minus e to the power minus 10s capital H. We're going to find the inverse Laplace transform of capital G and capital H, and then we're going to use our shifting formula to find the inverse Laplace transform of capital Y. If we can find small g and small h, then we can find small y. For capital G and capital H, we can use partial fractions. I'm going to leave this for you to check. Check that capital G is a half over s plus 1 over s plus 1 minus a half over s plus 2. And capital H is a half over s minus 1 over s plus 1 plus a half over s plus 2. Assuming these are true, you can also check that small g and small h are these functions. Small g is a half 1 plus 2 e to the power minus t minus e to the power minus 2t, and small h is a half 1 minus 2 e to the power minus t plus e to the minus 2t. Assuming these are correct, we can use our shifting formula to find small y. Because we've said that capital Y is capital G minus e to the power minus 10s hs. And using the shifting formula, this is the same as small g minus u10t small h at t minus 10. We know small g and we know small h. We can put these into the formula to find a formula for small y. Another example. Solve y double prime plus 4y is equal to u pi minus u3 pi with the initial conditions 0 and 0. Now our forcing function, u pi minus u3 pi, something like the function we started with at the start of the chapter. We have a function which is 0, then a function which is 1, and then a function which is 0. We take the Laplace transform of the differential equation and rearrange to find capital Y. I'll leave it for you to check that capital Y is e to the power minus pi s minus e to the power minus 3 pi s divided by s squared plus 4. we need to find the inverse Laplace transform of this function. But first, we're going to find the inverse Laplace transform of an easier function. As before, let's suppose that the exponential functions are not there. Let's suppose none of this is here. Instead, let's just guess that we have number 1 on the top divided by s squared plus 4. We will find the inverse Laplace transform of this easier function first, and then we will use the shifting formula to find the inverse Laplace transform of capital Y. So let's give this a new name. Let's use the letter h again. Let capital H be the function 1 divided by s squared plus 4. We can use partial fractions on capital H. And as always, I leave it for you to check that this calculation is correct. We should find that capital H is 1/4 multiplied by the Laplace transform 1 minus 1/4 multiplied by the Laplace transform of cos 2t. So of course, small h is 1/4 minus 1/4 cos 2t. Now that we know small h, we can move on to finding small y. And we can fit this in at the bottom of the page. It follows that the solution to the initial value problem is the inverse Laplace transform of e to the power minus pi s capital H minus the inverse Laplace transform of e to the power minus 3 pi s capital H. Using our shifting formula, this is the same as u pi small h of t minus pi minus u3 pi small h of t minus 3 pi. Substituting the formula for small h, we get 1/4 u pi multiplied by 1 minus, and then it's not cos 2t because we're shifting, it's cos 2 multiplied by t minus pi, or cos 2t minus 2 pi, and then minus 1/4 u3 pi, and then 1 minus cos, and it's not 2t because we're shifting, it's 2 multiplied by open bracket t minus 3 pi, or 2t minus 6 pi. The final topic for this week's lesson is the convolution integral. Let's suppose we have two piecewise continuous functions. That's functions where we can split our domain using a finite partition. On each one of the subintervals, the function is continuous, and all of the one-sided limits exist and are finite. Then there's a way to combine these two functions together into a new function called the convolution of f and g, and we use the star symbol to denote the convolution of these two functions. The convolution of f and g is the integral from 0 to t of, we need a new variable, I'm using the Greek letter tau, but we could use any letter here, f of tau g of t minus tau d tau. I'm going to put this at the top of the page because we'll be using this formula. So properties of convolution. F convoluted with G is always the same as G convoluted with F. F convoluted with G plus H is the same as F convoluted with G plus F convoluted with H. If we do G convolution H first, and then we do F convolution G convolution H, this is the same as doing F convolution G first, and then convoluted with H. And finally, if we have the zero function, if, for example, the function G is 0, integral of 0 is 0, of course, so F convoluted with 0 is 0, and using the first one, of course, 0 convoluted with F is also 0. I'm not going to prove these formulae. You can find it in your textbook or on the internet if you want to. I don't think it's relevant for us to sit and watch the proofs of these four rules. But I do want to do some examples. For example, cos convoluted with the function 1. Using the formula at the top of the page, this is the integral from 0 to t of cos tau multiplied by 1 d tau. The integral of cos is sine, so we're doing sine tau between 0 and t, which is equal to sine t. Then I want to calculate 1 convoluted with cos. The theorem says this should be the same, but let's do the calculation. Now we have the integral from 0 to t of the function 1 multiplied by cos t minus tau. Calculate this integral, we get minus sine of t minus tau between 0 and t. And when we evaluate this, again, we get sine t, as we should. One thing to note from this example is, in general, f convoluted with the function 1 is not equal to f. Here, cos convoluted with 1 is not cos, and 1 convoluted with cos is not cos. Next example, sine convoluted with sine. That's the integral from 0 to t, sine tau, sine t minus tau, d tau. We need to calculate the integral of sine tau cos tau, and we need to calculate the integral of sine squared tau. You know how to do this for calculus, so I'll just proceed with the calculation. And we end up with a half sine t minus t over 2 cos t. Something we can note from this example is, in general, f convoluted with f is not always positive. We look at sine convoluted with sine. Sine t is sometimes positive, sometimes negative. Cos t is sometimes positive, sometimes negative. So sine convoluted with sine will be sometimes positive, sometimes negative. Why are we studying the convolution integral in our chapter about the Laplace transform? Because of this very important formula. This is a formula that you would have already seen on your table of elementary Laplace transforms. the Laplace transform of f convoluted with g is capital F multiplied by capital G. This formula is going to be very useful when we solve initial value problems. Because when we're trying to find the inverse Laplace transform of a complicated function, it's very useful to know that the inverse Laplace transform, a product of two functions, capital F and capital G, is equal to small f convoluted with small g. And in fact, this is the formula that we want. For example, find the inverse Laplace transform of a divided by s squared plus a squared. There's two ways to solve this problem. We could use partial fractions using the method that we've been using before. But now we're going to use this more sophisticated method of using convolutions. First thing to note is that capital A is the product of two functions. The function 1 divided by s squared and the function a divided by s squared plus a squared. We know that the Laplace transform of t is 1 over s squared, and we know that the Laplace transform of sine at is a divided by s squared plus a squared. So, small h, which is the inverse Laplace transform of 1 over s squared multiplied by a over s squared plus a squared, is the same as the inverse Laplace transform of 1 over s squared convolution the inverse Laplace transform of a over s squared plus a squared. Anytime we want to do the inverse Laplace transform of the product of two functions, we can split this up into two inverse Laplace transforms as long as we put a convolution star in the middle. So that's just t convolution sine at, and we can calculate this using the integral form. To get at minus sine at over a squared. If we solve this problem using partial fractions, we would get exactly the same answer, but our calculation might take us longer. We can use the convolution integral to solve initial value problems. Solve y double prime plus 4y is equal to gt for any function gt with the initial conditions y of 0 is equal to 3, y prime of 0 is equal to minus 1. So let's proceed as we usually do. We take the Laplace transform of the differential equation and we rearrange to find capital Y. And we can find that capital Y is 3 multiplied by s over s squared plus 4 minus a half 2 over s squared plus 4 plus a half multiplied by 2 over s squared plus 4 capital GS. And by now you know why I'm taking a half outside and leaving 2 inside. Here it is at the top. Therefore, the solution to the initial value problem is the inverse Laplace transform of this function. We have 3 cos 2t minus a half sine 2t plus a half sine 2t convoluted with small gt. or we can write this in terms of the integral. And this is true for any g. We don't know what function g is, but we found the solution to the problem. Anytime we're given a function g, now we just stick this into the integral, calculate the integral, and we have our solution to the problem. We're almost finished. I told you this was going to be short. Find the inverse Laplace transform of 2 divided by s minus 1 multiplied by s squared plus 4. We're trying to find the inverse Laplace transform of the product of two functions. And I choose to split it like this. I'm putting the 2 in the left bracket because 2 over s squared plus 4, we know what this is. And we know what 1 over s minus 1 is. We know that this is sine 2t convoluted with et, or the integral from 0 to t, e to the power of t minus tau, sine 2 tau d tau. We can take the factor of e to t to the power of t outside the integral. We're just calculating the integral of e to the power minus tau, sine 2 tau, and we can use integration by parts to calculate this. And we get our solution, 2 over 5 e to the power of t minus 1 over 5 sine 2t minus 2 over 5 cos 2t. Again, we could have solved this problem using partial fractions. The calculation would have taken a little bit longer. Here we're using the convolution integral, and then the only time-consuming bit really is to use integration by parts to calculate this integral. And then final example of today's lesson. Solve for double prime plus y is equal to gt with initial conditions y0 is equal to 3, y prime of 0 is equal to minus 7. We take the differential equation and we put the Laplace transform on everything. This is the same as 4 multiplied by s squared capital Y minus s at y0 minus y prime at 0 plus capital Y is equal to capital G of s. Putting in the initial conditions and then rearranging and then rearranging again. 4s squared plus 1 capital Y is equal to 12s minus 28 plus capital G. Take a factor of 4 out of the left side. Rearrange, we get 12s over 4 s squared plus a quarter minus 28 over 4 s squared plus a quarter plus capital G over 4 s squared plus a quarter. Or we could write this as 3s over s squared plus a quarter minus 7 over s squared plus a quarter plus capital G 1/4 divided by s squared plus a quarter. Let's break this up so that our typical functions appear. We want functions which we can find on the table of Laplace transforms. S over s squared plus a quarter is on the table. A half divided by s squared plus a quarter is on the table. So we write this as 3 multiplied by s over s squared plus a quarter, minus 14, a half over s squared plus a quarter, plus a half capital G of s multiplied by a half over s squared plus a quarter. The first bracket is the same as the Laplace transform cos t over 2. And these two brackets are the same as the Laplace transform sine t over 2. We want to find the inverse Laplace transform of this function. The first two terms are easy. We can take the inverse Laplace transform of these straight away. For the third term, we used convolution formula. We can write that the solution to this initial value problem, first of all, 3 cos t over 2, that's easy, and minus a quarter sine t over 2, and then plus a half small g convoluted with sine t over 2. And I'm going to choose to leave the solution like this. And in less than 40 minutes, that is the end of this week's lesson. I hope that I've not given you too many difficult ideas this week, and you could follow the important ideas from this week. That's the end of our chapter about the Laplace transform. That just leaves one more chapter for the last 3 weeks. We're going to be talking about systems of first order linear equations. When we study systems of equations, we're going to be using a fair bit of linear algebra. Before next week's lesson, please quickly revise your linear algebra material. We're going to be using matrices, linear independence. We're going to be talking about the Wronskian. We're going to need eigenvalues and eigenvectors, etc. So have a quick look through your linear algebra lecture notes or your linear algebra textbook and just remind yourself of these ideas. Final exams will probably be announced soon. The discussions at the moment. It's going to be in mid-January. Let me check. I think it's going to be between the 11th and the 22nd of January. And our final exam will probably be on a Thursday at roughly the same time as our lesson, or maybe like the midterm exam, it will be at 12:30. And I'm guessing that it will be in the second week of exams, although that's not finalized yet. Are there any more questions? I'm in the middle of reading your exams. I finished question 1 and question 2 for everybody, so that just leaves question 3, which I'll try to read today or tomorrow or Saturday. And then you should expect your results either late tonight or tomorrow or Saturday or Sunday. You should expect to see your results.